SwayamPrabha. Digital India. Educated India.
Welcome back to this next lecture in the course on diffusion in multi-component solids. Last few classes we have been solving diffusion equation for various boundary conditions including those related to infinite solid-solid diffusion couples, carburizing, and also the instantaneous planar source. Now we will look into boundary value problems which include finite boundary conditions or periodic boundary conditions, and in today's class we will consider another industrially important process called homogenization. So, most of the alloys when they are cast they exhibit some kind of segregation. There are two types of segregations: macro segregation, which is on a macro level, on a bigger scale, on the component level, and a micro segregation, which is at the micro level or at the microstructure level. The macro segregation is something which we cannot get rid of, but the micro segregation, which invariably occurs in most of the alloys after solidification, has to be gotten rid of, and homogenization is often used in order to get rid of the micro segregation. Now, this homogenization treatment is governed by the process of diffusion, and so it is important to understand the various parameters which are basically driven by the diffusion. How the segregation takes place? So, for example, in casting there is something called as coring effect, due to which the solute content in an alloy varies from center of the grain towards the exterior. Very quickly, this is the part of the phase diagram, and this is the liquid region, alpha solid phase. This is the liquidus and this is the solidus. So, if any alloy solidifies, as it starts solidifying, the first solid that solidifies has a lesser solute content, which is given by this, let us point A. As it solidifies further from here, the next solid that forms is little richer in the solute, which is the composition concentration is given by A prime, and so on. So, if you look into the grain, the solute content varies from the center of the grain towards the exterior. Since the center is depleted in solute, if you draw the concentration versus x coordinate here, you will get a plot something like this, and when there is a next grain nucleated next to the first grain, this pattern will be repeated, and you will see there is a kind of a sinusoidal distribution of the solute throughout the microstructure, considering we are dealing with a single phase alpha. Of course, if there is a second phase, then there will be an interphase, the concentration profiles will be different, but right now we are considering only single phase. Now, to start with, or immediately after the solidification, the concentration profile may not be exactly sinusoidal like this, but there will be some kind of repeating variations, and as the homogenization start quickly, most of the time it will take the shape of a sinusoidal form. So, to start with, the distribution of concentration is given by this sinusoidal pattern. So, we will solve the diffusion equation. If I consider component I in an n component alloy, I have to solve the diffusion equation dou Ci by dou T for an n component system. Let us first write the simple continuity equation. Dou Ci by dou T is equal to minus dou Ji by dou x, and we know Ji in an n component system is expressed in terms of n minus 1 interdiffusion coefficient. So, J equal to 1 to n minus 1 dij tilde n dou Cj by dou x. So, if we substitute for Ji, we get a coupled diffusion equation, and as we have seen before, if we use the matrix approach, it simplifies the problem. So, if we write this equation in the form of matrix, we can write dou T by dou T of matrix C equal to, and if we substitute for Ji, we get d tilde n dou 2 by dou x2 of C, and we know this matrix C is a column matrix. So, for example, if we expand this for a ternary, we have two independent concentrations. So, this is a column matrix of C1 C2, and d tilde n is the matrix of interdiffusion coefficient. For a ternary, we need 4 interdiffusion coefficients. So, we have a 2 by 2 matrix. So, this is the diffusion equation that we need to solve, and what are the boundary conditions? So, the initial condition is here. Initially, we have a sinusoidal pattern. So, we can represent for a component I Ci at any x at t equal to 0, and the sinusoidal pattern can be represented as Ci bar plus beta 0 I sin pi x by L, where Ci bar is the average concentration. So, if we draw a sinusoidal pattern here again, the Ci bar is the average concentration about which the oscillations of concentrations occur. Beta 0 I is basically the amplitude of the pattern for component I, and 2L is the period of the pattern. So, L is half the period. So, this is x equal to 0, x equal to L, x equal to 2L, and this repeats. So, we have a periodic boundary condition. And what is the boundary condition? This is the initial condition. For boundary condition, we know, since this is periodic boundary condition, we know at x equal to 0, x equal to L, x equal to 2L, and so on, the concentration will not change. It will be same as the average concentration Ci bar at any time t. So, Ci at x equal to 0 at any time t equal to Ci at x equal to L at any time t, and so on, should be equal to Ci bar. And there is one more condition. We know as the homogenization proceeds, the variation in concentration should slowly die down, right, and ultimately we should get a uniform composition throughout the alloy. That uniform composition will be the average composition Ci bar. So, we can write Ci at any x at t equal to infinity should be equal to Ci bar. Now, these conditions also we can write in the form of matrices. So, if we write this initial condition for each of the component, and if we write them in the matrix form, we can write the matrix of C at x and at any x at t equal to 0 should be equal to C bar plus sin pi x by L times matrix of beta 0, where C bar, if we expand for a ternary system, should be C1 bar and C2 bar, matrix of the average concentrations of components 1 and 2, and beta 0 is the column matrix of amplitudes of component 1 and 2, which we denote as beta 0 superscript 1 and beta 0 superscript 2. Similarly, we can express the boundary conditions in the matrix form as C at x equal to 0 at any time t should be equal to C at x equal to L at any time t should be equal to the matrix of C bar. And we have one more condition which also can be written as C at any x at t equal to infinity should be equal to C bar. Okay. So, we got the diffusion equation. Let us denote this equation 1 in the form of matrix, and which we have to solve with respect to this initial condition and these boundary conditions. Okay. So, we first need to decouple the equation, for which we use the similar approach that we used previously for solving the multi-component diffusion equation, and that is we need the similarity transformation matrix, which we call P, for the interdiffusivity matrix. So, we define the similarity transformation matrix P, which is the matrix formed by arranging the eigenvectors of d tilde column by column. So, for ternary will be 1 beta 1 alpha 2 1. So, and for simplicity we write the eigenvectors such that the diagonal elements are normalized to 1, and delta is a diagonal matrix of eigenvalues of d tilde, and we know that P inverse times d tilde n times P gives us the matrix delta. Now, we convert the concentration from its original basis to cap basis, and we do that just like what we did for the diffusion couple problem. We pre-multiply the matrix C with P inverse, which would give the matrix of concentration in new basis, we call it cap basis. So, P inverse times C gives me C cap, and C cap again for ternary if we write is nothing but C1 column matrix of C1 cap and C2 cap. These are the concentrations in the new basis, that is cap basis. Similarly, if we pre-multiply by P inverse, it is called P inverse times the matrix of beta 0 gives me the matrix of beta 0 cap, which is again a column matrix of amplitudes in the cap basis. So, beta 0 1 cap, beta 0 2 cap. Now, with this, if we pre-multiply the diffusion equation 1 with P inverse. We know P inverse times C is C cap, and we have on the right hand side P inverse times D tilde. Now we smartly insert the identity matrix P times P inverse in between, right. So we have P inverse times D tilde times P, and the P inverse times C gives the matrix C cap. Since we are assuming constant interdiffusion coefficients, so we can take the matrix P inside the derivative. So what we get after pre-multiplying, equation 1 by P inverse and inserting the identity matrix P times P inverse appropriately, what we get, dou by dou T of C cap equal to P inverse times D tilde times P times dou 2 by dou x2 of C cap. And so this P inverse times D tilde times P is nothing but the matrix delta. So we can write dou by dou T of C cap is equal to delta times dou 2 by dou x2 of C cap. We can do the similar operation for the initial and boundary conditions. So for the initial condition, which is written here, if we pre-multiply by P inverse, we get C cap at x and t on the left side. Right side P inverse times C bar, we call it as C bar cap, the average concentrations in the new basis, cap basis, and P inverse times beta 0 will be beta 0 cap. So we can write the initial condition as C cap at x and C cap at, this is initial condition, so this should be t equal to 0. C cap at x at t equal to 0 should be equal to C bar cap plus sin pi x by L beta 0 cap. And the boundary condition, again if we pre-multiply by P inverse, this will be P inverse times C, which is C cap at x equal to 0 at any time t. This is C cap at L and T should be equal to C bar cap. C cap at 0 t should be equal to C cap at LT should be equal to C bar cap, and the last condition can be written as C cap at x t equal to infinity should be equal to C bar cap. So if we expand this equation in terms of the individual components, right, we get an equation of the form dou Ci cap by dou T should be equal to di times dou 2 Ci cap by dou x2. Similarly, if we write the initial and boundary conditions in terms of the individual components, we will see that Ci cap at x and 0 should be equal to Ci bar in cap basis plus beta 0 I cap sin pi x by L. Ci cap at 0 t should be equal to Ci cap at Lt should be equal to C bar cap, and Ci cap at x infinity should be equal to Ci bar cap. What we are assuming here is the period L is same for all the independent components, which should be the case usually, right, the way the microstructure evolves. Now we need to solve this equation, and we have periodic boundary conditions. So far we used Laplace transforms, which was useful for solving the diffusion equation with infinite boundary conditions. And now we will use another approach which is useful in solving the diffusion equation with periodic boundary conditions, and that is the principle of separation of variable. So, what we assume is that Ci cap at any x and t can be expressed as a product of two functions, one which is the function of only x, and the second which is the function of only t. So, let us call it x of x and t of t. So, Ci cap at x and t can be given as x of x times t of t. So, this means I can write dou Ci cap by dou t is equal to, since x is only function of x, so I can write x of x, and since t is function only of t, so I can replace dou t by dou t as the ordinary derivative d t by dt. Similarly, dou 2 Ci cap by dou x2 can be written as, since t is only function of t, can take it outside, times I can replace the partial derivative with again ordinary derivative, because x is only function of x. So, I can write d2x by dx2. So, this derivative with respect to t we usually denote with dot on top of the function, derivative with respect to s we denote by prime. So, double prime for second derivative. So, if we substitute this in the diffusion equation, what we see is x times t dot equals to di times t times x double prime, and if we rearrange we get t dot over di t should be equal to 1 over x times x double prime. Now, this is interesting, because what you see in this equation, the left hand side of this equation is function only of t, and the right side is function only of x. So, left hand side and right hand side are basically independent of each other. So, this equality will be valid only when both the sides equal to a constant. Let us call that constant as minus lambda square. So, we basically get two ordinary differential equation, one only in t, the other only in x, and those I can write as t dot plus di lambda square t equal to 0 and x double prime plus lambda square x equal to 0. The solution for the first one can be expressed as t equal to t naught exponential minus lambda square dit, and solution for x can be expressed as x is equal to a prime cos lambda x plus b prime sin lambda x. If we substitute these solutions in the respective equations for t and x, you will see they will satisfy the two equations. So, the function C I cap at x and t can be written as, I can combine these constants t 0 and a prime to a and t 0 and b prime to b. So, I can write a cos lambda x plus b sin lambda x times exponential minus lambda square dit. Now, we know the linear combinations of solutions is also a solution. So, if there are infinite number of values of lambda n for which the solution is satisfied, then their summation should also be a solution. So, I can write C I cap at x and t as the summation of a n cos lambda n x plus b n sin lambda n x times exponential minus lambda n square dit plus a term a 0. This a 0 is basically the value of a n when lambda n equal to 0. Now, this is the general solution that we have obtained for C I cap. Now, we need to find this constant. If we use this condition, C I cap at x infinity equal to C I bar cap, C I cap at x at t equal to infinity should be equal to C I bar cap. If we substitute t equal to infinity in this equation, exponential minus infinity is 0. So, we get a 0 equal to C I bar cap. If we use the initial condition now, C I cap at x and t equal to 0 should be equal to C I bar cap plus beta 0 I sin pi x by L. This should be equal to, if we substitute t equal to 0 for the general solution for C I cap, we know a 0 is equal to C I bar cap plus sigma n equal to 1 to infinity a n cos lambda n x plus b n sin lambda n x, and exponential 0 is 1. Now, if we evaluate this again at x equal to 0, so C I cap at x equal to 0, t equal to 0 should be equal to C I bar cap, and in terms of the general solution here should be equal to C I bar cap plus sigma n equal to 1 to infinity sin 0 is 0 and cos 0 is 1. So, this is the summation of all a n's for n equal to 1 to infinity. What this essentially means is sigma a n should be equal to 0. Now, this, if this has to be true for all values of a n, then all a n's should be equal to 0. Then only this will be true. So, we have eliminated one term from here because all a n's are 0. So, we can write C I cap at x 0 should be equal to C I bar cap plus sigma n equal to 1 to infinity Bn sine lambda nx. Now, I use the second boundary condition, that is at x equal to L, that is Ci cap at L and T should be equal to Ci bar cap, and if I substitute in this, I get this should be equal to Ci bar cap plus sigma n equal to 1 to infinity Bn sine x is L. So, lambda n times L. Again this means summation of Bn sine lambda nl equal to 0. So, either all Bn's have to be 0, which will yield a trivial solution, or the second term has to be 0. See, this sine term will be 0 when? Yeah. So, whenever lambda n is equal to n pi by L. So, we have lambda n is equal to n pi by L. So, Ci cap general at x and t will be given by Ci bar cap plus sigma n equal to 1 to infinity Bn sine n pi x by L times exponential minus lambda square, which is minus n square pi square by L square dit. Again, if I write at t equal to 0, this should be equal to Ci bar cap plus beta 0 I cap sin pi x by L, which is from the initial condition, and if I substitute x equal to 0 here, should be equal to Ci bar cap plus sigma n equal to 1 to infinity Bn sine n pi x by L. So, this Ci bar cap will get cancelled. So, I get beta 0 I cap sin pi x by L should be equal to sigma n equal to 1 to infinity Bn sine n pi x by L. Now, to obtain the values of Bn, what we do, we multiply both sides by sin m pi x by L and integrate within the interval minus L to L. Here m is an integer. So, we get beta 0 I cap integral minus L to L sin pi x by L sin m pi x by L dx should be equal to summation of all the integrals n equal to 1 to infinity. Bn's are constant, so I can write integral minus L to L sin n pi x by L sin m pi x by L dx. Now, it will be clear why we did this, because the integral on the right hand side, if you look at it, it has a value equal to 0 if m is not equal to n, and it has a value of L if m is equal to n. Similarly, on the left hand side, it is a similar integral with n is equal to 1 here. So, this has the value of 0 if m is not equal to 1, and it has a value of L if m is equal to 1. So, in effect, if both the sides are 0, then it will not help. So, what happens is m has to be equal to n and m has to equal to 1. So, we should have m equal to n equal to 1, and in which case the value of the integrals will be L. So, I can write this equation as beta 0 I cap times L should be equal to, only for n equal to 1, b 1 times L. So, basically we get b 1 is equal to beta 0 I cap and all other b n's are 0. So, we got the solution for C I cap, which takes the form C I cap at x and t should be equal to C I bar cap plus b n should be equal to b 1, which is again beta 0 I cap sin n is equal to 1. So, sin pi x by L times exponential minus pi square d I by L square t. And we can see, if we write for all independent components, this can be expressed in the matrix form as matrix of C cap is equal to matrix of C bar cap plus sin pi x by L times the matrix exp. I will define soon what is the matrix exp, times the matrix of beta 0 cap, right. And this exp is a diagonal matrix with these exponential terms along its diagonal. So, for a ternary system, this is exponential minus pi square d 1 by L square t 0 0 exponential minus pi square d 2 by L square t. So, we got the solution for the concentrations in the cap basis. Now, we want to convert back to the original basis. So, we do a reverse operation. So, if we pre-multiply both sides by the matrix P, right. So, P times C cap will be the original matrix C, the matrix of original concentrations. P times C bar cap would be matrix of C bar. So, we get C equal to C bar sin pi x by L times, again this would be P times exp, but if we insert P inverse times P in between, we get P times beta 0 cap, which should be equal to the matrix of beta 0. So, P times the matrix exp times P inverse times the matrix of beta 0, and this is the solution that we have got for homogenization in an n component alloy, for which the initial concentration profile was represented by the sinusoidal form. So, for binary, this will reduce to, if we just, for binary we need just one concentration variable. So, we can denote it by C, C equal to C bar plus beta 0 sin pi x by L, this P and P inverse both will be 1 times exponential minus pi square d by L square t. and typically this exponential term is written in the form of exponential minus t by tau, right. So, this is written as c bar plus beta 0 sin pi x by L exponential minus t by tau, where tau where 1 by tau is basically pi square d by L square, and it has a unit of per second. 1 by tau has a unit of per second, d is meter square per second, L square is meter square. So, this is basically a measure of rate of homogenization. So, we can see the rate of homogenization depends on the diffusivity. Higher the diffusivity, higher will be the rate of homogenization, and it varies inversely with L square. So, the rate of homogenization will be higher for smaller period. So, if we have two different segregation patterns with the same amplitudes, but if they have different periods, the segregation pattern with lower period will homogenize faster. Okay. So, this is the solution that we have obtained. Now, let us study the features of the concentration profiles that develop during homogenization in order to understand how the homogenization proceeds based upon the solutions that we have derived. Let us first consider for binary and then also for a ternary system, so that we will understand how the cross diffusion term make important effects. So, let us first consider the binary case. So, this figure shows the concentration profiles that developed at different times of homogenization in a binary alloy, and the parameters that we have taken for the simulation are the diffusivity is 3.2 times 10 to the power minus 15 meter square per second, which is 0.0032 micron square per second. The period is taken as 100 micron or L is equal to 50 micron. The amplitude is 0.25 atom fraction and the average concentration is 0.7 atom fraction. So, this blue profile is the initial concentration profile. The average concentration is at 0.7 and the amplitude is 0.25. So, the profile is oscillating between the maximum value of 0.95 and the minimum value of 0.45. This is at t equal to 0. If we use the equation that we derived and simulate at different times, at 8 hours the profile is represented by this red curve, at 32 hours the profile is represented by this green curve. We can see as the homogenization time proceeds, the amplitude keeps dropping. So, the fluctuations are getting lower and lower. So, with time the profile is tending to flatten out. If we consider a particular period and let us look at the two sides of the half of the period. On the left side you will see the curvature of the profile is negative, and for constant diffusion coefficient we know dou c by dou t equal to d times dou 2 c by dou x 2. If the curvature is negative, means dou c by dou t is negative, which means the concentration should drop. Whereas, on the right side of this half interval we see the curvature is positive, and so the concentration should increase with time. At x equal to 0, L, 2L and so on, the curvature is 0, and so the concentration should be constant, which is the average concentration C bar. Okay. This was the effect of time. Now, let us understand the effect of period and the diffusivity. We know the rate of homogenization 1 by 2 was given by pi square d by L square. So, the rate is inversely proportional to L square. So, obviously, as the period increases, the rate of homogenization should decrease. So, again these are the concentration profiles with the similar parameters that we used for earlier profiles. The same value of diffusivity beta 0 and C bar, and at t equal to 8 hours we have simulated for different periods. So, this at t equal to 8 hours, this is the profile for L equal to 100 micron, the red one is for L equal to 50 micron and the green one is for L equal to 25 micron. So, after the same time of homogenization, although we started with the same amplitude and the same average concentration, we see that the profile with the lower period homogenizes faster. Then obviously, since 1 by tau or the rate of homogenization is pi square d by L square, as the diffusivity increases, the rate of homogenization should also increase, and it is shown in this profiles here, again with the same parameters at t equal to 8 hours and the half of the period 50 micron. For different values of diffusivities, the profiles are shown here. So, blue one is for d equal to 3.2 times 10 to the power minus 3 micron square per second. This one is for the double the diffusivity, and the green one is for 4 times the original diffusivity. And we see as the diffusivity increases, the homogenization rate is increased. So, this was for binary. Now, let us look into a ternary profile. Now, ternary means we have two independent concentrations. So, the two concentrations can vary independently, third one will be just a dependent component or will just respond to the variations in the first two. So, the average concentration that we have taken for the ternary is 0.5 mole fraction of C1, 0.25 mole fraction of C2, and amplitudes for the two are 0.2 mole fraction of C1 minus 0.2 mole fraction of C2, right, which means C1 and C2 are varying in the opposite direction. So, this is the pattern for C1, the initial profile for C1, and this one is for C2. So, C1 is varying from the maximum value of 0.7 to the minimum value of 0.3 periodically, and C2 is varying from, in the same interval, the minimum value of 0.05 to the maximum value of 0.45. And you can see C3 is constant throughout. So, to start with, there was no variation in C3, it was uniformly distributed. Okay. Now, one would tend to think, since C3 is constant, it should remain constant throughout the homogenization treatment, but that is not true because of the cross effects. Although the gradient in C3 is 0, but there exists gradients in 1 and 2, and so the cross interdiffusivity term would come into effect. Right. We need 4 interdiffusion coefficients for ternary. So, the values that we are used, assuming of course the constant values are given here. D11 is 4.5, D12 is 0.3, D21 is minus 4, D22 is 1.7, and the values are in 10 to the power minus 3 micron square per second. Now, we see we have simulated the concentration profiles at different times at t equal to 8 hours, 32 hours, 64 hours and 196 hours. As we go at 8 hours, we see the amplitudes of 1 and 2 have decreased, and interestingly C3 to start with was constant, but it has now developed the undulations. As I increase the time, the undulations have C3 have increased. C1 is homogenizing very fast. Of course, the main diffusivity of component 1 is much higher compared to the main diffusivity of 2. So, C1 is homogenizing much faster. And as I go to 64 hour, what we can see, C1 has completely flattened out, but C2, which looked to be flattening out between 8 hours to 32 hours, has now reversed its undulations. and this is the interesting effect which has occurred because of the interactions. Now, we will try to understand how. Okay. Now, to start with, if we look at the D21 and D22 value, D21 is very highly negative and it is the magnitude is higher than the main coefficient of 2. So, we expect that interaction of 1 on 2 will be great, but we can see because the flux of J2 is given as minus D21 3 dou C1 by dou x minus D22 3 dou C2 by dou x. The gradient of 2 is also high to start with. So, both the gradients are higher and C1 is flattening out very fast. So, the interaction effect of 1 and 2 are not very obvious here, right, and by the time C1 has flattened out, the gradient in C3 has picked up, and so the interaction of 3 on 2 have come into effect. Now, to understand those interaction, I need to convert this matrix. This matrix is represented with component 3 as dependent. I can convert it to a matrix with component 1 as dependent, because we want to analyze 2, 3. So, if I convert it to component 1 as dependent, this is the matrix that we have got, and what we see, D32 is much higher than D33. It is negative and an order of magnitude higher, and so the interaction of 2 and 3 becomes very important. At the same time, the gradient of 3 was very low to start with, and that is the reason. So, if you write the similar equation for G3 in terms of D23 and D33 with component 1 as dependent, we will see, although C3 was flat to start with, but there was a gradient in 2 and which caused the development of undulations in C3, right, and by the time C1 has flattened out, C3 has developed a profile, and now the effect of 3 on 2 would come into picture, and we can see D23 is almost similar to D22, and that is why the undulations of C2 have reversed in this case. If you compare to start with, and here the direction of undulations have reversed, and slowly this will flatten out. So, this is very important in ternary and higher order system. This cross terms plays important part. If we do not consider these cross terms, we would have missed this effect, the undulations that have been developed in C3. Now, where would this be very important? For example, if C3 was constant initially, and let us assume that it was below the solubility limit of 3 in the alloy, but since these undulations developed, and if it happens that this concentration tries to exceed the solubility limit of 3 in the alloy, then we expect the second phase to precipitate out. So, if we ignore these effects, we would completely miss the second phase precipitation. We will wrongly predict the microstructure. This is just one example why the cross terms are important. Okay. So, we have developed the solution for homogenization for n component system. We applied it to binary and ternary, and we also have seen the behavior of concentration profiles during homogenization treatment. All right. So, we will stop here for today. Thank you.